All right, let's talk briefly about the history of calculus. You may be familiar with the fact that Sir Isaac Newton gets the credit for inventing calculus. He wrote a paper in 1669, but for some reason he refused to publish it. So, independent of Newton, um, Gottfried Wilhelm Leibniz um, also worked on the same ideas and published a paper in 1684. And when that paper was published, there was a controversy then because Sir Isaac Newton was like, hey, that was my idea. And so he was able to prove eventually that he invented it first and he gets the credit. But Leibniz also independently invented calculus uh, and finally published a paper in 1684. Now, the notation that we've been using for a derivative actually comes from Joseph Louis Lagrange and wasn't introduced until around 1749. So this notation f prime of x was actually invented by Lagrange. Okay, at the time that Newton and Leibniz invented calculus, there was no such thing as a function. The idea of a function was not a thing. So this f prime notation that we've been using was invented later. Now, the Leibniz notation, well, maybe I should back up. Now, Newton, we don't use Newton's notation for a derivative, right? He didn't have an idea of there was no such thing as a function at that time. And so he just put a dot above y. And that was the notation that Newton used for a derivative. But the notation that Leibniz invented is very useful because it reminds us what the derivative is. So if you recall, the derivative of a function at a point is essentially its average rate of change, and the average rate of change is just a delta y over delta x, right? Now this, I should make a note here. This is a comma. This is not a prime symbol. So I should probably delete that. All right, so we're looking at the change of y over change in x over an interval. That's the average rate of change. And as the change in x gets smaller and smaller and smaller, we get the derivative of the function. And so this dy over dx is meant to remind us that the derivative is the change in y for an infinitesimal change in x. Okay, that's what the d. So we're using a d instead of a Greek letter delta, the triangle. We're using a d, and you can think of the d in dy dx as standing for an infinitesimal change in the quantity. Right? That just means that it's infinitesimally small. All right, so let me write that. I'm gonna spell it right. Infinitely small. That's what infinitesimal means. It's infinitely small. All right, so that is the Leibniz notation for a derivative. And sometimes we use d over dx as an operator. This is an operator. So this is something that's performed on things. Like a plus is an operator. It adds two things together. A square is an operator, right? It takes a number times itself. So we can think of this d by dx, all right? It's not dy dx now, it's d by dx as an operator, and it's basically the derivative of x squared. Okay, so we can also write it that way. So, given that information, let's take a look at example 1, which we just have a bunch of different derivatives given with different notations, and we want to circle the ones that are correct. All right, so I'm going to actually, as I look at this, I can see that I probably should have said, okay, let's call this y. So we have a function g of x. G of x is 1 over x, and I could also give the output a variable y. All right, so if y is g of x and g of x is 1 over x, then which of these notations is correct for the derivative of that function? Well, okay, we're familiar with this one. This one is the Lagrange notation for a derivative. So that's definitely true. Let's look at b. All right, we're using a prime symbol, but it's not. We've got x prime, we got 1 over x prime. So we're looking for the derivative of 1 over x, but the derivative of 1 over x is not 1 over x prime. That doesn't work, so I'm going to cross that one out. That's not valid. All right, here we're using the operator d by dx and applying it to g of x. So it looks a lot like this, right? And so this is valid. We could put here we put x squared. Here we've just got g of x. So we got the derivative of, we got an operator applied to g of x. So that's good. All right, so here we have dy by dx, dy over dx times 1 over x. All right, this looks a little like an operator, but this is not an operator, right? This is the derivative itself, right? So this is not an operator. All right, because if it says dy dx, that's just the derivative. So this is saying that it's the derivative dy dx times 1 over x. That's what that is, and that is not the same thing as the derivative of g of x. So I'm going to cross that one out. Here we have the operator d by dx applied to 1 over x. All right, so this is basically saying take the derivative of 1 over x. So this is good. This works. All right, well, I'll meet you for the next example.